So first of all, Jeremy, congratulations on winning the Opir challenge, being the second winner. And I understand you had quite a few attempts, but the solution that you ended up with, I think, was the most unique and the most amalgamated in terms of taking various techniques and kind of combining them in very creative ways. So I got to ask, what's your background? Is it in security?
Yeah, so my background, I actually started as a front-end engineer, so building websites and kind of getting my roots in that. That led me to learning that data teams and data science orgs needed front-end apps. So that was kind of my intro to the data and ML world, and I fell in love with it. I learned all about modeling and data sets and kind of understanding what that was. So I had done a military career before that, got out, wasn't really the career path for me, went into defense. So I was working for Lockheed Martin, and they have some main core business areas. They do space, they do helicopters, they do airplanes. So I ended up joining a team within that group that was kind of a consultancy for a lot of those business areas. When they had data problems, they would come to this team. So I got to work on all sorts of fun stuff, but everything from ballistic missile detection to rotary blade detection. And the data sets were multimodal at the most. So a lot of it was vision and data. We got into like predictive maintenance. So, every time they would do oil changes and they would notice defects, they would have some text data, and we were trying to predict when's the engine going to blow up, because there was kind of a lead time in the supply chain. So that's a bit of my background from there. After Lockheed, I kind of moved into the startup realm and more into the tech scene. So looking at multimodal embeddings and vision language models to impact e-commerce. We noticed, like, if you go to wayfair.com or something like that, and you search for a blue couch, you get pink couches and gray couches. So there's obviously a data issue there. So we were looking at, how do you leverage these tools and vision to, maybe annotate the data better or give better descriptions so that searching tools and recommendation tools can work better. Most recently, I've moved into cybersecurity. It's always been a passion of mine, figuring out like how to hack a system, how to protect a system. So right now I run a director of engineering position at Keeper Security. They're a privileged access management tools. So they do everything from secrets management, remote sessions, endpoint privilege management. And my job is to try to figure out how we can apply ML and AI techniques into the product. So a lot of edge compute, a lot of zero knowledge, zero trust constraints. So we're always building super small models that can run on the CPU, which is kind of a unique field, especially when the core AI scene is, giant data centers with giant models. We're on the other end of that extreme. So really enjoy kind of playing with the data modeling and the architecture work. But yeah, that's a bit of my background.
Yeah, I mean, I think there's a resurgence of these small models because people got a little bit trigger happy with, GPT 3.5 and onwards, applying it to everything.
Mm-hmm.
And then, people started to notice that, of course, if you apply it to everything, there's going to be slowdowns. And you can deploy it in ultra secure environments where you need to self-host the models or things need to be air-gapped. Have you always thought that you need small models along with the large language models?
I think the small model bug bit me when I was at Lockheed. We were tasked with building models that would be deployed on a helicopter. So helicopters are pretty tight for space. They need to carry people and products, and computers are kind of secondary. So you have your avionics systems, but we wanted to run as many ML models as possible. So there was detection and flight systems and radar systems. And at that time, there was the NVIDIA Orin system, the X series, and we had like a 4 gig GPU. So it was like, how many models can you run on a 4 gig GPU? And we pushed the limits of that. A lot of the times we learned that a transformer model doesn't need a GPU. If you train it small, you reduce the hidden layers, you can kind of squeeze that thing onto a CPU, and it runs under a second. We weren't trying to do like millisecond real time. That's what the GPU was really good at. But we were looking for like 1 or 2 second inference speeds. So that was kind of the initial bite of the small language models. At that time, they weren't really labeled as small language models. They were just like build a BERT model, build a masked encoder, build a classifier, build a prediction. Now they've kind of got a little bit of a surname to them, but same idea. You build a really tight encoder that matches your data set, and you build a little decoder that you can build a task on top of, whether it's regression or classification, or next token prediction, and kind of stepping into the language modeling. So I've been experienced with the small language space for a bit, since like early 2017. That was kind of when we first kicked off some of those. So before all the craze about it, and now you've got, the fine tuning of the SLM world, we were, training BERT models on predictive maintenance data, trying to figure out if this O-ring is going to fail in 2 years. So definitely our heads were in the sky on like what could be done with machine learning. I think at that time it was more classical deep learning approach, where now with some of the generative AI, I'm sure their data sets are just growing like crazy, because the challenge we were struggling with was our corpus of data. You only had 10 years of data, or sometimes for the newer platforms, 2 or 3 years. So encoding that and figuring out what the actual model around those features would be, we didn't have a lot to work with. So the models were okay, but they were really difficult to explain. Some of the longevity decisions that we made from there were difficult to back. So that was kind of the early challenges. I'm sure today they're, a lot more mature in that way, a lot more explainable. But definitely small language models have been kind of our bread and butter in that space because of the deployment targets. It's always an edge deployment. It's always lightweight CPU, lightweight RAM, lightweight GPU. We did end up running like a 12 gig GPU, which back then was like, wow, this thing's huge. Now it barely runs like a 3 billion parameter model. But that was kind of the constraints that we operated within. So at Keeper, we have a similar problem because we have to hold this zero knowledge concept. That's a principle for our products. And what that means is we can't actually know what the user's data looks like. It has to be encoded if we store it. It has to be encrypted if we store it. So inference is a really tough problem. How do we build a model, one, that targets their space, but two, can run on their hardware? And we can make assumptions that they have a modern computer with like a modern CPU, maybe a GPU, but all of the models we're producing are CPU bound, which is a really tough task. So we're like 100 megabytes and smaller, less than 20 millisecond cold starts, 1 to 5 millisecond inference times is kind of where we shoot for. And then building a task and a data model around that constraint is just a huge challenge. So we're always prying at the latest tech and the latest classifiers and latest encoders to figure out, can we use this for what we need?
Jeremy, I'm really interested, as a follow-up, you said you got the small model bug bit you at Lockheed. And I guess I'm curious how you view an approach to the sort of testing you did against the Opir model, how that would differ if you were going up against a much bigger model. Like what, from a mindset perspective, what are you doing differently?
Yeah, so a lot of the times when I approach a model, the core math constraint is, how does the tokenizer look at the data? In our case, we were building a prompt injection model ourselves, and then I saw Opir launch. I'm like, this is a great model. It's a multitask model. That's kind of what we were wanting to build anyways. So like, awesome architecture. But the first thing that comes to mind is, what's the tokenizer doing? What's the vocabulary? What's the tokens going to represent? Because it doesn't matter what classifier heads you train or anything like that. If the data is kind of unknown, I know your classifier is going to be broken. And that was kind of where my mind went when I was attacking at that model, was, you said it's multilingual. What about the craziest multilingual tasks? And one thing that we found was, the further we push into multilingual, the further the vocabulary doesn't represent that data. So you end up with a bunch of unknown tokens, and generally that last layer, the classifier head, has never been trained on unknown tokens. You can do some reinforcement learning and kind of tune it in, but it's a difficult task, because what if your whole string is unknown? Now I can bypass your classifier because it doesn't know. So it's kind of an obfuscation technique. And we had that problem at Lockheed when it came to acronyms. You know, a lot of the military does acronyms for everything. It's 50
PLAs, 3-letter acronyms, as the military runs on them, right?
Vocabulary doesn't split an acronym up really well. Sometimes you get like 1 or 2 tokens. Sometimes it just goes to the unknown category. So we were trying to build regression models on that to try to predict, you know, is this data value going to change from like 0.9 to 0.7 over time? And the data that we were giving into it was just all unknown. So we had a lot of pre-training steps. We had to kind of teach the model the language that we wanted to learn. And in any multilingual model, that's the challenge. Your encoder doesn't know the language. And linguistics is a huge space, and there's PhDs and lifetime employees that kind of focus just on that. But models really struggle to represent language. You know, there's 3,000 in the world, so you can't capture it all. I just saw a NIST article from our mathematicians friends where they were proving that you can't make a model that captures every single possible vulnerability. There's a mathematical proof that says if you can think about it, there's a way around it. And I think you throw multilingual on top of that, and it's an impossible problem. So when I saw Opir was multilingual, I'm like, that's my target. I'm going to throw languages it's never heard of. So Intuit, which is an Alaskan tribe, they live all the way up north in Alaska. There's like 200 or 300 in there. They draw with symbols. They don't really have like a formal linguistics pattern. And I know no model really has encoded what that vocabulary looks like. So I can pass through and kind of trick the classifier head to say like, nah, you don't know what this is. It's unknown. And once I learned that that got through, I knew, okay, I've got an attack pattern that works. The tricky part after that was, how do I get the system prompt to be tricked? Because the system prompt is going to see this kind of unknown language and just throw it out. So it works for encoding and decoding model. It doesn't really work for a decoder only model because it's just outputting a bunch of unknown. And you know, most LLMs have been trained to just throw those away. So kind of attack one was get through the classifier by obfuscating my inputs and just tricking it, basically. You know, here's a bunch of unknown tokens. And once I learned the classifier wasn't really trained on unknown tokens, I could get through that safety mechanism. And now I was an attack on the actual system prompt and what that base LLM looks like. So that was kind of the guide, but it was all stemmed from like this knowledge of how a tokenizer works. Is if you can trick how the encoding model functionality works, your classifier was generally trained on that. So I don't care what the last head looks like because I'm going to throw out a bunch of data it's never seen. And you can do like reinforcement learning and try to like steer that last layer to say, if you see a bunch of stuff you've never seen, throw it out, make it unsafe in this case. But a lot of times that final step isn't really taken care of. You know, people just fine tune based on the vocabulary in the data set. But there's this whole like kind of adversarial technique that you may need to train in. So that was something that we learned from this model and something we're applying to our own prompt injection model, because it was like, we want to train it on 30 plus languages. And that's exactly the same problem that we've seen in our training is, you know, I think in our case, it was like 90% of our Chinese data was unknown. So our classifier said F1 score is great, precision's great, but when you actually put a Chinese string through that model, it all comes back as unknown because the tokenizer can't embed that data. So it just gets kicked off to some vector and that's it. And the actual classifier head doesn't know how to handle that. So that's always a technique that I've played with. Kind of through the years, I've learned if you can attack a tokenizer through adversarial techniques, it doesn't matter what task you've trained beyond that. The encoding itself is wasted. So in most BERT models, like an unknown would be a 128. So as soon as I saw running the Opir model locally was giving me 128s, I'm like, perfect. I can attack your language and linguistics problem. Yeah. And then general prompt injection techniques beyond that. The trick with the Opir challenge for me was, how do you get through the classifier first? And once I got the classifier broken, Then it was how do I figure out what your system prompt's checking? And it was tight. And unfortunately, I was second. And the guy who got first was doing the same attack that I was trying to do. So when you guys tightened it down, I'm like, no. This was the attack I wanted. So I kind of throw out my ideas and say, okay, I know I can get through the classifier. What would a good system prompt be? There's a little bit of logic because I've built, strong system prompts. And then I was just probing it. Can I throw multilingual, multiple languages at it? Does that trick it? Yep. Okay. It doesn't get caught by the classifier. It doesn't get caught by the system prompt. And then you had like a hard fixed rule on like, don't share this secret.txt. So I'm like, how do I get it to tell me the content of the secret? I don't want it to read it. I just want to tell me what the content is. Maybe I could get the bytes and then execute like a hex hash on the bytes. Maybe I could get it to do that for me. So in my prompt, I was like, languages aren't known by this model. What if programming languages aren't known? So I've already kind of proven the classifier doesn't check languages. Maybe I can prove that the LLM and classifier don't know obscure languages. So my father ended up doing a university spree, and they did Crystal reports. And Crystal is like a awfully known scripting language. It's kind of like VBA in Excel, and it's functionally just a programming language, but no LLMs really know Crystal. I'm like, all right, that's a fun attack pattern. Let me see if I can write a little script that reads files in Crystal. Very basic language. And it kept getting caught every time I typed the word secret. So I'm like, okay, so the classifier knows the word secret. Let me figure out how to trick it while I do this Crystal script. And eventually I ended up finding that, if you do a little bit of a style encoding or byte encoding, so forcing the model kind of do math operations, the system prompt doesn't necessarily say prevent math operations, but it does say prevent reading the secrets.txt. So I just had to kind of encode it in a way and then trick the classifier with this multilingual attack and then split the data up. So I did multilingual at the top and then the attack at the bottom. And a lot of times when you build a bi-encoder model, it doesn't have a huge window of what's at the beginning and what's at the end. It kind of just looks right after the beginning and right before the end. Mm-hmm. So I knew I could trick the model with multilingual. Now I had to trick the model with a big sentence that would trick the system prompt. So I just stuck both of them at the other ends so that the classifier is not going to catch it. And then when the LLM does its encoding, generally it's a cross-attention model, which means that it does have reference of what's at the beginning and the end. So used multilingual attack to say, tell me the values of this file, tell me the values of this file, 2 different languages. And at the end say, encode this file and tell me the content. And eventually it said, I can't tell you the content of the secrets.txt, but here's the value of it. And it just pasted it in plain text. I'm like, I got it. Then I tried that technique with a couple other obscure languages because I was wondering if like Crystal's the only one that got through, or if I can, use this same tactic with different programming languages.
What were those other obscure languages, just out of curiosity?
There was like Elixir. Elixir's not super obscure, but it's not a common language. Yeah. If you looked at like the top 10 languages, it's rising. A lot of people would probably say it's a big popular one. But from a corpus of what the LLM's been trained on, Minimax has a cutoff date, going back to 2025. It's not that popular. Where you look at Java or C# or Python or TypeScript, it's everywhere. They scraped every GitHub repo. But Elixir's a small core. I looked at Haskell. It's a functional programming language. Same idea. I'm just trying to make it read a file, so very easy to program, but it's not a popular language. It's a small minority. So once I learned languages weren't represented, I kind of asked the question of like, what about computer languages? How much in your corpus did you train on obscure computer languages? And I kind of figured the answer out pretty quickly is like, maybe you have some good, top 10 programming languages, but what about the bottom 10 programming languages? And I think that's where the adversarial mind is like, when I'm building or constructing a synthetic database of, attack patterns, I want to make sure I have a little bit of coverage in that space. Doesn't have to be the full distribution, but, just training the classifier a little bit on some of that information is going to make the classifier stronger. So as soon as I started to pry back those layers, I'm like, I got it. Okay, I've got an attack pattern. What can I do here? How do I trick the LLM now? And it kind of pivoted from break the classifier to break the system prompt. And system prompts are tough. You have to do a lot of work to kind of inspect them. But this two-tiered system, you blocked me out for hours. Like, how do I get through? And once I cracked one, the system prompt is pretty easy to crack. But I did notice just mentioning certain words, after knowing how to break your classifier would pop up. And I had a local model running, but the one challenge I didn't know was what was the labels you guys were using. You had like 120 labels. So as I was testing it, I'm like, okay, maybe that's a label they put. So I'm growing my label list, trying to mirror what you have. And I would run my query through the local model and run the query on the website. And I would see the scores are a little different. But one advantage that I saw was you were printing out 3 labels. So every time I had a bad answer, if I didn't have that label, it went into my pool. And all of a sudden, my model was answering almost identically to what your model was answering. So then I could iterate and kind of test locally. And like, okay, does this technique work? Nope, classifier catches it. Let me change this one word. Okay, it gets through the classifier. Go try that out on the system prompt. So there's a little bit of a hacky way to play the game, but I was specifically trying to do this like multi-pronged attack because I knew I could attack your tokenizer stack. That whole encoding model and what the classifier head was trained on, that was what I had to get through. So figured out how do I break that first, which was really fun. And the whole challenge idea and kind of building a test harness around that, I'd showed that to our team that was building their own, and like, we're going to have to figure out how to close the gaps on our model for this, because our challenge is to make a 70 megabyte prompt injector, which is incredibly difficult because you start throwing heads out at that point. You dump your hidden size down to like 300, and it just loses accuracy. And we want it to be as accurate as OPIR, but we don't want it to be big. So that's kind of the game that we're teetering. But yeah, such a fun model to figure out how to tweak and break. I had a blast with it.
I'm also really interested, Jeremy. I mean, you mentioned at the start that you lived in Australia for a little bit, and you've obviously moved around a bit as well. And obviously from Australia, like, we have this perspective of the American mindset being very much maximalist in approach. So like, if you look at things like Cerebras, for example, it's like, well, let's make a bigger chip. And it's a sort of similar approach with these LLMs. It's let's have a trillion parameter model. Let's have a bigger and bigger model. Do you think that your mindset from moving around and living in different places has helped you with your approach as well?
I think from a what can you do with the minimal resources perspective, that's where it's gone, is, traveling a lot, moving a lot with the military. It's always like, how do you maximize what you have? That was always kind of the core. I think that's translated to how I approach ML engineering. And one of the challenges that all these industries are facing is you need chips, you need data, you need people, you need time, you need money. Right? That's a pretty complex problem. How do you support that? And you see a lot of venture teams try to like dump money into it, but that doesn't solve the problem because you need the skills, you need the data. And I think that's indicator of maybe you're chasing a problem that's a little too far out. I'm totally on board for like the research minds, the big LLM boom that they said, let's just keep scaling it and see what happens. It turned out great, but there's a lot of cons with that system from a data center, from a power system, from a data perspective, that it doesn't scale anymore. So yes, you took an architecture and figured out how to make it incredibly generalized, and from a product perspective, it's changing the world. That's awesome, but there's a limit. It can't go beyond the limit, and we're maybe hitting a physics limit, maybe hitting a mathematical limit, but I think functionally we're hitting skills and data. We can only encode our knowledge, and maybe you can tap into futuristic tech or maybe tap into historical tech, but it's a limited knowledge space. So OpenAI came out a few years ago and said, our models aren't going to improve. We've already encompassed all the knowledge possible. So now you have to pay surgeons and expert PhD artists and all of these highly trained, highly skilled people to curate your data set. And
Yep.
that's difficult because those people probably didn't pick a path to say, let me train a computer. They picked a path to help people or to build businesses or to, be an artist. And they're not necessarily going to give up their, life's dream or passion to go label data for you. And I think that that's probably the core of that problem, where I kind of look on the other extreme as, give me 500 samples and tell me what I can do. If I can take weights and make those weights represent the data through a mathematical process, which I'm not a math wizard, it's just, generic loss functions. Can you get it to kind of align? And I always look at it as like a needle. Can you get it to point at the right number that it's supposed to point at? 500 samples, 1,500 samples, 50,000 samples. I mean, we're not talking huge data chunks. And you can all of a sudden get a little architecture to do exactly what you want. And I like that work a lot because it's cool, it's fast, and it's portable. Where the other end of the spectrum, you got to build a data center. You got to get a gigawatt of energy. You got to have a company and support and facilities to deal with that. And in the capital world, you want to make a product. One sounds very difficult. One sounds very easy. So I'm always on the easy side, keep it simple. A lot of the times it's a classifier. A lot of times it's a masked encoder. You're just trying to prove that, this small foundation can do the task you want. Yes, I would like a model that could be general because it's cool to see those, and it's cool that you don't have to like make a custom model that covers 1,000 different tasks. It just works with whatever task you give it. And that was kind of the approach that we saw when Opir came out was, okay, it's got like 1,000 potential areas and it's more of a zero-shot space. You could fine-tune that, make it even easier. But what if we needed to change the labels? Now you've got a data problem. Now you got a people problem. Now you got to retrain or pre-train even. And I think the easiest path is always like make it as simple as possible. Opir is huge. It's a big model. It's small, which is good. Small in perspective of other models. And it's tunable. And that's where I really like that class system as I was playing with it. It was like throw 10 classes at it and it works. Throw 120 classes at it. And maybe it gets a little distracted, but it works the same. And ultimately you're just trying to get a binary answer, safe or not safe. And categorize it up to that point. So I think my experience with like make what you can with what you have has definitely drawn through. Lockheed at most had 5 to 10 years of data. That's not much. And the data quality was really poor because you had 19 through 24-year-olds typing in on a computer, or even worse, writing on a piece of paper. So they weren't being accurate. They weren't thinking about, 5 years in the future, maybe a computer system would ingest this. And that was a really difficult problem. We didn't have much. So when we looked at our training, it was like a 90-10 split because our data set was just so obscure and discrete that we kind of had to just train the model on everything and overfit it. When I jumped into the e-commerce space, it was a very similar problem. Data was a very, very fragile piece. It was normally mislabeled. It wasn't really helpful and representative, and we didn't have a lot of it. Sometimes you could only scrape so many couches, and you could only get so many indicators or features about that couch. So how do you train a model around that? A traditional deep learning technique doesn't work. I want to just throw everything at the model and see if I can represent all the data and maybe fine tune it or reinforce, some output that I'm looking for. But just embedding it was difficult. So I think that that's kind of the core ideology that I hold is if you can build a strong embedding layer with what you have, your task is probably going to be good. Whatever downstream task you want, just get the base encoder sorted. With the large language models, the problem that I constantly see, and you'll see like posts of Strawberry has 3 R's or Strawberry has 2 R's. That's a tokenizer problem. It's how the word is being split and encoded, and you have to train the tokenizer for that. How many words are like that, though? How many tasks revolve around that? And when you start to go into the trillion parameter space, you can't have a handle on that. There's too many parameters to understand. And I think some research labs really try to focus on that problem, and they spend days and days and months just working data sets. If you can tune that data set up, you could train a better encoding model. But what some of the scaling models and like the Grok papers were showing, if you just let it think forever, the math will eventually average out and you get some benefits. So it's split on the research side on like what's the right way to play this game, is throw all the data and don't care, let the model's architecture figure it out, let all the hidden layers sort out those problems, or sit with the data and make it perfect. And when you're at that scale, you're talking years, millions of dollars of investment just to make something that might be better. On the other extreme, you're talking 1,000 samples that you can generate with ChatGPT in 10 minutes, and you can make something that probably beats at the task level those bigger general models. And you can make 100 of them and deploy 100 of them. But that's a different orchestration problem than the other team has. So I love the idea, make what you can with as little as what you have, but I personally would love to go explore the other extreme. Say I have in the world petabytes, because I'm sure the challenges from a software perspective are difficult. How do you label everything? How do you ensure quality of everything? And are they doing that today? Probably unlikely, but definitely an interesting perspective to look at it from. Of growing up with kind of a lighter weight family unit and a lighter weight system, we just made do with what we had. I think a lot of my logic towards model development is kind of in the same regard of, we didn't have a huge home every time. We didn't have 100 boxes worth of stuff, but we enjoyed life and we made it work and we used what we had. And then you moved and you had a different task and you had a smaller portion of things. But the research labs, I'm sure, love massive data centers, because it's fun. So,
Alex, did you have any questions as well? I mean, Jeremy's obviously been very comprehensive with his answers.
Yeah, well, just a few comments. Jeremy, thanks for your findings, because those help us train the next version of Opir and then release that to the public as well. And of course, it gives us ideas on how to, go around the unknown issue, which is maybe flag stuff that outputs a lot of 128s. Maybe that's like the simplest way to classify something as unsafe, is it's almost all unknown. And the model can't really decide what to do with it. So it gives us a lot of ideas. So thanks for being comprehensive with your attempts as well.
Yeah, it's definitely like, I just went over to our team and I said, hey, I found Opir doesn't work here. Our model's going to have the same problem. And we did an analysis just today, and all of our data set, English encoded great, every language, it was like 70, 80, 90%. I'm like, so we either pre-train a tokenizer to work better, or we work that classifier problem and say, your whole text string is unknown. Maybe it's not supported, and we're going to deem that unsafe. Maybe it's not a true answer, but from a task perspective, if someone used a language we didn't expect, I can't make a decision. So my classifier is going to say that's an unsafe process, which is an easy fine-tuning problem. But just having that mind space of like, okay, there's 3,000 languages. We're only covering maybe 70 in our training data set. How do you handle the other 2,930? That's because that's going to be an attack vector that someone might exploit your classifier on. And kind of getting ahead of that, you can build a better data model around it. So it's always fun to play the adversarial card against models, because there's one element where you're like, I want to get it to learn the task, get the weights to work, get the output to be where I want. And then you throw the adversarial card in there and it's like, oh, you can just trick it and make it do whatever you want. So how do I add that into the model? Which is, it's tough from a data perspective, but if you start looking at the tokenizer output, it makes it very simple because everything that doesn't fit will come out as looking the same. So start putting a label to those inputs. And
Yeah, absolutely.
I'm excited to see the next iteration of this.
Yeah, us too. And the other two winners also had some ideas that, well, they sparked some ideas for us. But I think your attempts were a lot more creative, and gave us even more vectors that we should look out for. But taking things to the extreme, what do you think the future of AI security looks like if we get, for example, thousands of bots trying to attack a system and just trying everything that they can, similar to how you did it, but like times 1,000? What does AI security look like in that mode, in that era?
Yeah, it's a topic near and dear to my heart. Obviously, from a perspective of like AI attack bots or a botnet, maybe we see that in our next decade. I think from the knock perspective, and the SOC perspective, the concept of having an AI partner that can move at the same speed as those AI attackers. We're kind of moving away from like, a human, maybe in the 80s, like a human would hack into the mainframe, and, in the early 2000s, botnets and worms really big. We're moving into this next era where if you can trick Claude into doing something, spin up 10,000 sub-agents and, go attack the NSA. How's the NSA protect themselves? How's a country protect themselves? There's got to be another feasible, scalable problem on the other end of that. Can a firewall show up with powered rules? Can you have confidential computing where maybe these deployments are isolated and it doesn't matter what an AI is going to try to attack or probe? It's protected all the way through. And I also think there's a component from a red team or a pen testing perspective that it's only going to be easier for them to figure out how could you attack this. And maybe the bad guy, the black hats, aren't able to get in because the white hats and the purple hats and the red hats are attacking themselves, and they've got incredible tooling to do that. I still think there's going to be like infrastructure problems, DDoS sort of attacks, flooding attacks, botnet attacks are still going to exist. It's going to be easier to make those attacks. But on the same light, if you can secure your environment and kind of understand those threat boundaries, doesn't matter what's coming at you, because you can block those IPs. You can say those requests are too fast and just shut them down. I think there will be a lot more creative exploitation of known vulnerabilities. So people who don't upgrade their systems or didn't know that there was a vulnerability, I think those are going to be the targets for a lot of these attackers to go look at. Scan this website. Oh, cool, I found a couple open ports. Probe them and see what version. Maybe run an attack to figure out what version you have. That version's immediately going to connect to a CVE that they're going to go exfiltrate data through or run root on. And that's moving faster and faster. I think that's the scariest part about this is you could have a swarm of AI agents working to go be the enemy here. From a nation state perspective, I think a lot of your critical infrastructure, I'm talking about your SCADA systems, all of your core infrastructure for telecoms, even your power management, they're huge targets. Because have they ever been hooked up to the internet? Have they ever been updated? And what about those 0 days that no one knows about, that AI might be able to detect or find? The recent news about this Fable 5 and Mythos model, almost being labeled as a cyber weapon. Anybody can just type a prompt and potentially hack. And that's scary, maybe a little bit of fear mongering through that, but I think that that's where the future is going of these models, is maybe they uncovered that it's possible. It was possible 3 years ago. People were uncensoring models and doing this, but now the agentic abilities allow it to propagate through different systems and try different techniques. And I think the combination of those are really opening up the security vulnerability. We're always laboring as like AI threats are scary fast. Human threats happen still; they're not going away, but AI can move sometimes at 2x, sometimes at 400x the speed. Depends on the attack vectors. So it's a scary world. I wouldn't let the fear get to it, but I do see a huge product need for the same AI-powered tooling as a defensive technique. AI-powered tools for firewalls, for system alerts, for analyzing logs, and those have to be as real-time as possible. So kind of going onto that small language model space is maybe Opus or Fable isn't the right call to build a automated threat detection tool, because you're going to pay the latency costs, and it has reasoning and thoughts, and it's going to work through that problem. But you build a little classifier, little BERT model, modern BERT model, all of a sudden instant results, and you can classify in real time, and maybe those signals help you shut the systems down before the swarm of bots come after you. And they're very lightweight to run, so you could run 100 of them on a simple EC2, and almost build this giant firewall or guardrail between you and those attackers that might come in. So definitely an area I'm excited about. I love building in that space. I love having a job that we get to actually deliver some products that bring value to the world in that way. But within the open source world, I think the core is going to be how much data could you collect that represents all those challenges? Because will you ever get data sets that represent the NSA or another intelligence agency in a country? Probably not. So can your model adapt to those needs, through a zero-shot technique, or do they have to then fine tune on top of it and, kind of keep propagating those weights for their needs? So definitely a cool spot, but yeah, it's a good question of like, where's the security going? Is it automated attacks from here on out and we're just suffering, or do we have kind of a defensive automated system that traditional deep learning ML models can play in, but as well as some of this generative AI to try to surface some of it? I think your sysadmins and SOC members, they don't want to look through logs anymore. They've done that for 20 years. A summary, an email, Slack notification is huge, and even that little signal could help stop an attacker in its track. And looking back 5 years ago, those were big selling points for companies. We can do a push notification. Now AI can just say, yep, here's an email, and it's perfectly worded in whatever language you want, and it's sent to a huge distribution group all agentically. I think that's really cool. It's a fun time to be there, but you got to have kind of the defensive layer first before that nice to have system exists.
Yeah, and with bots, fighting bots, it's kind of fire against fire, but there's also an unfair advantage with spinning up a swarm of social engineering agents that have voices attached, and them calling every employee in the company to try to find someone's human weakness instead of the bot weakness.
Mm-hmm.
And in that case, I think that might be even scarier when these bots sound like humans and can attack us, socially engineer us.
Yeah, and you're even seeing some of this stuff where the C-level executives or even strategic executives at companies are getting cloned because they do talks, they do conferences and videos, and in 30 seconds I could clone my CEO and I could run an attack, right? So there's kind of this mass deception technique, and it really erodes the trust of, is that him? Did he really say that? And when you start to interface with maybe some sensitive data like company emails or phone numbers, yeah, social engineering is a very scary world, because as teams have moved remotely, is there a face-to-face? Pretty unlikely. Is there an email or Slack message? That's a great attack target. Let's figure out how to figure out, if I can send a message as the CEO or the CTO to say, go turn a rule off. Now I've got a little bit of a play. But I think we're going to see that from attacking perspectives. We're also going to see a rise in scams, unfortunately, where people are going to have hyper personalized scam techniques applied to them. Maybe they're going through relationship issues or financial issues, and attackers are going to be playing on those cards at a scale that we've not seen before. We've already pushed the boundaries on that, just humans playing that role. But what if you had a swarm that could research and learn and do whatever open source intelligence on those victims, and all of a sudden the attack works way better, and it's automated and it scales? That's a really scary world to be part of. So I see the duality that's coming in. The big providers are trying to build the guardrails and protections, kind of prompt injection tools, content and toxicity tools, to maybe prevent some of those challenges that might show up if it was completely unguarded. And then the open source world is like, let's pull off all of those rules and make this thing completely obliterated and uncensored, because we earn that, and it's open source and it shouldn't be managed. And you see that from different nations. I think the US has an interesting AI culture, but you'll see the Chinese labs, the Singapore labs, Australian labs, even Canadian labs. They all kind of have their own little bias, unintentionally sometimes. Maybe it's how they were raised or their cultures or religious beliefs, but you'll definitely see a trend with models kind of steering towards certain tasks and steering away from other tasks. So I think from an offensive and defensive perspective, it's an interesting play to, how do you trick those models to do what you want? How do you trick those models to defend against the people who do that? And that's where I think, Opir and other NER and classifier stop models really help out.
That's an interesting aspect. The social engineering models because of their country's bias.
Mm-hmm. Yeah, and I've seen this from the EU perspective. It's a conglomerate, so you have all sorts of religions and ethnicities and backgrounds and cultures, and the bias that gets applied to a EU-focused or Europe-focused model is they try to generalize across that. But Eastern Europe is very different than Western Europe, and Northern Europe is very different than Southern Europe. And they have different tastes and different decisions, different religions. And, it's hard to fit a model, a general, language model around those problems. Maybe you don't train as much on Islam as you do Catholicism, right? And maybe if it's an Italian, AI developer, it's not going to have as much Nordic information, because they don't know those cultures. They don't know all the rules about those cultures. And that's just one little enclave, which spans many cultures and systems. You get out of the US space and you look at South America or Africa or Eastern Asia, you get all sorts of differences, religions, people, heritage, history. And I think models really struggle to represent kind of that world knowledge in a safe way. A lot of the US teams might, collect all the data and then apply their instruction-based tuning that's mainly geared towards answering questions correctly to an English speaker. Is that the same instruction tuning that you would expect for a Chinese speaker? Maybe, maybe not. Maybe their culture is different. Maybe the answers are expected to be different. So it's an interesting problem when you try to build like guardrail models and prompt injection models on top of that, because maybe your model didn't consider those biases, and maybe the model's being put in front of a Australian company's model instead of a US model, and your idea of how English was represented or how people will talk to it was wrong. And I think outside of any like philosophical points or beliefs, encoding that data is very difficult. That's an incredibly complex data model, and it goes back to that scale problem of what's the expert say? Where do you get an expert that can answer those questions? Do you have like an allegiance of all the experts from every country manage labeling data? I don't think they're necessarily going to go take that job unless you pay them $1 million. But politicians and religious leaders and mathematicians and education teams and artists, they all kind of bring a little flavor of bias to their knowledge space. It's a fun problem. I'm sure big research labs struggle with this because they have a corpus of data, and how do you tell if it's biased or not? the person asking that question has a bias. And if you send it to, another guy on the team, they have a different bias. So it's, I think trust and safety is a tough area within the LLM and SLM world right now. But if you just focus on a task, you can probably build a pretty decent representation of what the task requires. It doesn't really matter anymore about what language you bring in. Is the task, detecting prompt injection. And it's a little less biased in that knowledge space versus building like a big general model that could, accomplish classification or any other task that you ask it to without that fine-tuning technique. Yeah. But great question. Yeah.
Nice. Yeah, great answer. Sam, did you have any more questions?
No, it's been fascinating though. So thanks very much for your time, Jeremy. It's been really, really interesting.
It was great talking to you guys and meeting you. I loved the challenge. I thought it was such a fun idea, and it was hard. It actually pushed me to a limit, and I really had to kind of like, how do I break this thing? And after like 70 tries, I didn't get through. I'm like, how do I break this thing? What do they got going on over there? And, so it's been fun to play around with it, but I love the architecture. I love the concept. Building like a binary decision model with this multitask layer with different tiers is it's really novel. So I really enjoyed the architecture and the model design, and the corpus of data you've trained it on. I mean, it took me a long time to figure out how to break through that. And every traditional attack technique, every traditional language process that I threw at it, it was just getting blocked over and over. Until you really understand why it was getting blocked and step out of that boundary, then I could break it every time. But you really gave me a run for my money on that. So it was a great model.
That's great. I'm glad it was a real challenge, and thanks for breaking it, because we learned a lot.
The website was great. I loved the design and the idea, and just the interface was really well executed. And I just kind of the grassroots nature of that eval experience.
I try to make it look like a Pip-Boy screen, or
yeah,
one
definitely had a little that Fallout vibe.
Yeah. Okay, Jeremy, thanks so much, and I hope you're enjoying your 3 billion tokens. Or the
Yep, I hit my daily rate limits every day. I ended up using a lot of. I wanted to set up a Hermes agent, so I'm like, all right, perfect. I'll go build out a custom provider, get everything wired up, and it's been fun. I'm using Minimax 2.7 for most of it.
Good.
And, 3 days later, I've got a whole system that I can fire tasks off, and got a whole loop engineering idea and a whole, almost AI company running on that thing. So it's quite cool to leverage it for that.
Nice. Glad it's useful.
Yeah. Cool. Well, thank you guys for having me. I really appreciate the talk today. Let me know if you want to chat more. I can always collaborate. And
we definitely would, and we'll see you on the next one, hopefully. So, yeah.
Cool.
Yeah, maybe. Jeremy, thanks a lot. It was an awesome conversation.
I appreciate it.
See ya.
Yep,
Bye.
bye.